So my name is Christopher Thiele. I'm a graduate student in computational and applied mathematics here at Rice University. And today I want to talk about how to improve the scalability and performance of linear system solves in a Pore scale simulation. And this is a joint work between the Chem department at Rice and Shell. So first I want to talk about the motivation, what our application is, and why linear solver performance is important to us. And then I want to go into two different approaches to speed up linear solvers. The first one is an algorithmic approach, a mathematical approach, whereas the second one deals with the efficient implementation of iterative solvers using asynchronous and one-sided communication. So what is our application? We want to solve or simulate the phase separation of a fluid mixture. So as you can see here, we start with an initial random distribution of two fluids, red and blue in this case, in our computational domain. What you see here is not actually the fluid, but the interface between the fluid. And as time progresses, you can see that these interfaces simplify, the fluids separate until we reach an energy minimizing final state, where we have only one fluid on either side of this interface. In order to simulate this process, we need to solve a nonlinear system of equations in each time step, and we're using the Inexact Newton's method to do that, so we have to solve multiple linear systems in each time step, which is why linear solver performance is important to us. So the first approach to improve this linear solver performance would be, that I want to talk about today, is hierarchical scale separation, which is an algorithm to speed up the linear system solves given a particular discretization, which is, in our case, a discontinuous Galerkin method with a modal basis. For example, we use a piecewise linear discontinuous approximation. So in these pictures here on the left, you can see such a representation of a function here with two elements. So you can see it's piecewise linear. And given that we have a modal basis, it's very easy to split this into a piecewise constant part, which is here in the center, and the remainder, which is just the slope in each spatial direction. So you can think of the one in the middle, the piecewise constant part, as the average or scaled average over each element. And when you sum up these two, the piecewise constant and the slopes, you get back your original solution. So now let's have a look at the matrix structure that we get from such a discretization. We have an example here with three elements in 3D. You can see that E0 and E1 are not connected, and therefore the corresponding parts of the matrix here are empty. And each of the other blocks has low order components in red here, and higher order components, which are the slopes in each direction, which are blue here. So in 3D we have three dimensions, so three slopes, which is why we have three of these blue unknowns in each, for each element. Now we just reorder this matrix to get all the low order unknowns to the top of our solution vector, which is the red part, and all the high order unknowns to the bottom. We reorder the matrix accordingly. And as you can see, each of these blocks still resembles the original structure of the linear system. And from now on, I will just denote all the parts of the solution in the matrix that are related to low order parts with a bar. So we have A bar, X bar, B bar, and I will use a hat to refer to those parts that correspond to the higher order components of the solution. So we have A hat, X hat, and B hat in blue, and the yellow matrices are just coupling terms between these two layers. So now what we do is we split the linear system into two. So this is an equivalent formulation. If we have a solution X that solves both these linear systems simultaneously, it will also solve the original system. Furthermore, we can split this large matrix A hat into a block diagonal part and an off-diagonal part, which we move to the right-hand side here. And we can simplify the right-hand side. So after some matrix vector products and vector updates, we just get a regular right-hand side vector. So we have these two linear systems. And of course, the lower one here, since it has block diagonal structure, this is really just a set of very small decoupled linear systems. So we can write it this way. We have our reduced size coarse scale system here. And for each element, we have one such small system here. So remember, it's the slope in each direction. So these would be 3 by 3 systems in case of our piecewise linear approximation in 3D. So this equivalent formulation of the linear systems leads us to the original hierarchical scale separation algorithm, which just starts with an initial guess. then computes the right-hand side up here, solves for x bar, the piecewise constant part of the solution, plugs that into here, gets the right-hand side, solves for x hat, and iterates between these two linear systems until the solution converges. And that has been introduced by Dimitri Kuzmin in this paper in 2014. And we introduced two modifications to this algorithm. First of all, we only approximate the coarse scale solution x bar up here. And then we perform this fine scale solve down here multiple times in each HSS cycle. So what we do is we start again with an initial guess. We compute the right-hand side. Then we only approximate x bar here, compute the right-hand side here, solve for x hat, and immediately plug it back into the right-hand side, solve for x hat again, and iterate over this several times before we get back to the coarse scale. So we have two parameters to choose here. First, the accuracy with which we approximate x bar in the coarse scale system, which is why we call it inexact HSS, because we only approximate the solution here. And then the number of fine scale solves down here in each HSS cycle. So we applied this algorithm to linear systems from the fluid simulation I showed earlier. And we compared just a plain GMRes solver versus the same GMRes implementation embedded into this inexact HSS scheme for a system with up to 67 million degrees of freedom. And we observed a speed up of up to 9 times here. And it looks like the speed up is even increasing with the problem size, which is, of course, very promising. So now let me get to the second part of my talk, which is about the efficient implementation of iterative solvers using asynchronous communication. As many of you will know, these linear systems can become very large for large-scale simulations, so we can easily have hundreds of millions or even several billions of unknowns. And in that case, even a single matrix, a single sparse matrix, will occupy hundreds of gigabytes or even terabytes of memory. So we need to distribute it over many computational nodes of our cluster. And the easiest way to do this distribution is to just slice the matrix and all vectors. So here we have an example where we have n computing ranks. Each of them has a subset of the vector entries of each vector. So these y1, yr, yn would be smaller vectors, and a subset of the matrix rows. And for rank R to compute a sparse matrix vector product, which is the most expensive operation in solvers such as conjugate gradients or BCG step, we would have to compute these smaller matrix vector entries, matrix vector products, and sum them up. So we'd have to multiply this with this, this with this, and plus this with this. So it's really just a regular matrix vector product. And as you can see, we can decompose this into a fully local part, ARR times VR, where all the data that we need is already present. So no communication between nodes is required. Whereas the remaining part here requires the remote vector entries VI that need to be communicated over the network. And hence, we want to overlap that with the computation of the local matrix vector product. So we tried to implement this in an efficient way using asynchronous and one-sided inter-node communication, as well as a hybrid parallel programming pattern. So we use processes as well as threads. We try to avoid any kind of implicit synchronization, both between processes and between threads. And we did not use a fork and join threading model, so we don't fork and join before and after each operation, but we fork once, do the entire linear system solve, and join in the end. To do this, we used the GPI2 PGAS library, which is an open source asynchronous PGAS library, which is developed at the Fraunhofer Institute for Industrial Mathematics in Kaiserslautern, Germany. And of course, such an asynchronous communication library only helps if we have asynchronous algorithms. So let's have a look at different algorithms to compute the sparse matrix vector product. So here for each algorithm, you can see 2 arrows. The upper one represents what we call communication threads. Those are the threads that take care of the internode communication. And more specifically, the yellow part is the preparation of the communication. So you need to look up the vector entries that need to be communicated, accumulate them or copy them to one contiguous send buffer before you can actually send them to other nodes. That would be the red part. That would be a call to the communication library, GPI in our case, or MPI in other cases. Then the dashed line refers to the point where we wait for the communication to finish, which is a synchronization point, at least between threads. And then the blue and green part is the actual computation. The blue part is the local sparse matrix vector product, and the green part is the remaining SPMV, which of course depends on the communication to be finished. So the synchronous algorithm is really naive. We just prepare and initiate the communication, wait for it to happen, and then do all the computation at once. Then we have the semi-asynchronous, or what we call the semi-asynchronous algorithm, which overlaps the actual communication. So the preparation here, the yellow part, is still done sequentially. Then we prepare and perform the communication while we already compute the local sparse matrix vector product. Then we wait here before we actually need the remote data. And finally, we have the fully asynchronous algorithm down here, where we even overlap the preparation of the communication. So while we copy the vector entries to a contiguous send buffer, we already start the computation. And notice that is something you can only do with a hybrid parallel implementation, because otherwise each of your processes will have to do this preparation, so it cannot do anything else at the same time. But here we only use 1 or 2 threads to prepare this, and all the other threads already start the computation. So we implemented all 3 of these algorithms in a library called GasPLS, and we also compare against Trilinos, more specifically the hybrid parallel conjugate gradients implementation within Trilinos. And we applied all of these solvers to linear systems, again from our fluid simulation, which have a band diagonal structure with around 60 to 70 non-zero entries per row. And we used an unpreconditioned conjugate gradient solver simply because we're only interested in computational performance rather than convergence, at least for these experiments. So here you can see a scalability plot for a system with about 500 million unknowns. We start at 8 nodes and scale up to 80 nodes. So nodes means physical computing nodes in our clusters. So you have to multiply this by 24 to get the total number of CPU cores, which would be something around 1,900 for 80 nodes. Yeah, you can see that the asynchronous algorithm scales very nicely. We get up to a speed up of about 9 when we increase the computational resources by a factor of 10. The blue line is the synchronous algorithm. It is less efficient, as you can see. The semi-asynchronous one would be somewhere in between. You can see the full results in this paper. But we do see an additional speed up and an increase in time to, or an increase in performance by overlapping everything, even the preparation of the communication. The yellow line is Trilinos. We included it here because it's one of the few hybrid parallel packages out there, and it's what we use in our simulation. As you can see, it does not scale that nicely in this experiment, but that is because the hybrid parallel implementation within Trilinos is in its early stages of development, so there will be quite some improvement in the near future, I believe. They are aware of these issues and they want to introduce asynchronicity as well. Okay, to summarize, we looked at 2 different approaches. The first one was the Inexact HSS method, which shows promising speedups compared to using a regular Krylov solver. It's robust with respect to the parameter choices that we can make, and it may even serve as a black box solver for discontinuous Galerkin discretizations in the future. We also looked at the asynchronous conjugate gradient implementation from GasPLS. It displays a high, strong scalability and helps to reduce time to solution in our linear system solves. And future work may include the integration of preconditioners to the core scale solver within Inexact HSS, as well as the performance analysis for higher order approximations. We use piecewise linear, we could use piecewise quadratic or even higher order. And of course, a mathematical convergence analysis for these algorithms. And also the development of GasPLS continues at the Fraunhofer Institute, and they will add more solvers and preconditioners, and it will soon be released as open source software. So thank you for your attention.
We have time for questions.
With multigrid?
Yes, there is a relation with so-called p-multigrid, where you do not refine with respect or coarsen with respect to your spatial discretization, but with respect to the polynomial approximation order. So P multigrid would start, say, with a piecewise quadratic approximation, then the next level would be piecewise linear, and then piecewise constant. And HSS is derived from a special case of P multigrid with only 2 levels, but the decoupling between these two is more complete. And of course, there are also HP multigrid methods where you start with a P refinement in the polynomial approximation order, and then you use H refinement, your usual geometric or algebraic multigrid on the bottom level once you achieve, once you reached piecewise linear or piecewise constants. We just used the default GMRES implementation.
So on what test case did you use for your computation? Is it a regular meshes or it's unstructured DG based? But how is your test case? Is it homogeneous, regular?
Yes, it's we used a full domain, which is the unit cube in our case, and we have a regular hexahedral mesh.
So how, in the case where we have HP refinement or a regular mesh, how is your algorithm's behavior?
Well, we didn't do HP refinement in our case. I just mentioned it because that's where HSS was derived.
But this is my question is how it will be affecting the communication and all the asynchronous behavior of your algorithm.
Yeah, it's hard to do H refinement in this particular application because the grid is kind of fixed. We cannot really refine it because we have a porous domain, a model for or a scan of this porous domain.
See, if you don't have H refinement, you will have to do some domain decomposition with parameters, for example. And the number of elements per subdomain will not be the same. So how will it be affecting your computation?
Yes, that would be interesting to see as well. At this point, sophisticated or more sophisticated domain decomposition has not been integrated into the simulation and thus not in these experiments.
Very good. Any more questions? No? So thank you again.